we built the most advanced scientific instrument in human history, a $10 billion time machine. Our goal was to see the beginning of the universe. We saw it. But that success has now become science's greatest crisis. Webb found things in the first moments of the universe that should not exist, while the Milky Way has been producing stars for 13 billion years. Webb discovered galaxies that had already completed their life cycles when the universe was only 2 billion years old. This is a paradox. We measured the expansion rate of the universe, and found two different, conflicting results. The 9% difference between them is not an error. It's proof that the model itself is broken. But it's not these numbers that are truly disturbing. The real paradox is that our best instrument is proving our most fundamental theories are wrong. If this chaos of information excites you too, subscribe, because now we're embarking on a journey into the cracks of science. We're beginning. The scientific community had a solid story about how the universe works. A story built over decades, tested by dozens of telescopes, called the Lambda, Cold Dark Matter Model. According to this model, the formation of the universe was a slow, arduous, and generational process. Billions of years of growth, collisions, and mergers. That's why scientists built the James Webb Space Telescope, to confirm this story. But when Webb looked into the depths of space, everything changed, because what it saw fundamentally shook everything we thought we knew. To understand this story, you first need to know the old and accepted one. We can call it the cosmic construction timeline. According to this calendar, the universe began 13.8 billion years ago, in a point of unimaginable heat and density. In fractions of the first second, space itself expanded faster than light. Within the first few minutes, the first atomic nuclei formed. But the universe's truly interesting era was just beginning, because for the next 380,000 years, the universe was a glowing fog. It was too hot and dense for light to escape. Then it cooled. The fog cleared. Light filled the universe for the first time. We can still detect this ancient light, the cosmic microwave background. Even today, this is why this timeline wasn't a guess. It was a measured reality. After this clearing, gravity took control. Hydrogen clouds slowly clumped together. These clumps grew denser, and perhaps 200 million years after the Big Bang, the first faint stars began to shine. The key word in this timeline was slowly, because it was thought that galaxy formation could not be rushed. But the James Webb Space Telescope was designed to look at this exact period. The telescope would observe the universe when it was only a few 100 million years old. The expectation, therefore, was to see faint proto-galaxies, chaotic gas clouds, the scattered raw materials that would one day form the universe we see today. On July 12, 2022, NASA released that first photograph. In a patch of sky the size of a grain of sand held at arm's length, thousands of galaxies shone. However, there was a problem. The galaxies in the photo were not chaotic. They weren't young and inexperienced at all. On the contrary, many were massive, structurally mature, and extremely bright. They looked as if they had been growing for billions of years. Yet, the light that reached Webb had started its journey when the universe was only a few 100 million years old. There just wasn't enough time. You can think of it like watching a time lapse of a skyscraper's construction. you know the rules. First the foundation, then the steel skeleton, then the floors. The process takes 2 years, but now, imagine hitting play and seeing the 50th floor completed in the first 30 seconds. The lobby has marble floors and people are eating lunch. You wouldn't say the building was impossible. You'd think there was a problem with the tape. This is exactly what Webb gave scientists in the summer of 2022, a tape that didn't match the construction schedule. That's why some researchers unofficially started calling these galaxies impossible galaxies. Not because they defied logic, but because according to our current model of the universe, there was no physical way to build them that fast. This was not a single exception. It was the beginning of a pattern. Because, in the following months, the data stream continued. More galaxies, more structure, more things that had no right to be where they were. The research papers, initially cautious, grew bolder over time. Phrases like challenges current models gave way to titles like requires a fundamental revision of galaxy formation theory. But among all these discoveries, there was one special galaxy that forced scientists to stare at their screens and ask aloud, "What happened?" How is this possible? Its technical name is long, so researchers simply call it GS9209. And what Webb confirmed about this galaxy in 2023 shook the astronomy community in a way no discovery had in years. Because this galaxy was dead. In astronomy, a dead galaxy is one that has stopped forming new stars. It has run out of fuel. But the problem wasn't where GS9209 died, but when it died. According to Webb's light, this galaxy had formed the vast majority of its stars in a window of about 800 million years. And it did all of this within the first 1.8 billion years after the Big Bang. While the universe was not even 2 billion years old, it had lived its entire productive life and fallen silent. Feel the scale of that. Our own galaxy, the Milky Way, is still forming new stars today, approximately 13 billion years after its birth. But this ancient galaxy had done everything it was going to do, formed hundreds of billions of stars, and then shut down completely, before most other galaxies had even properly started their operations. This is why it's not just one strange data point. It's the herald of a model's failure. Webb continued to find multiple mature, finished galaxies in similar situations, galaxies that had no right to exist in that epoch. This left scientists with two choices. Either something was wrong with our model of galaxy formation, which would require rewriting the textbooks, or something was wrong with our understanding of the early universe, which would require something even more disturbing. Scientists proposed a mechanism to explain this, the quenching of star formation by supermassive black holes pushing gas out of the center. This mechanism is known to exist. But the problem was whether it could happen early enough and fast enough to explain what Webb was finding. The math didn't quite line up with the existing models. These cracks in the models were only the beginning. Because within these cracks, a much older mystery was hiding, one that scientists knew about even before Webb was launched, a mystery so profound that Webb has now made it impossible to ignore. There's a clock that governs everything in the universe, and this clock is not just ticking. It's also expanding. This is the ultimate clock of the universe. When astronomers say the universe is 13.8 billion years old, they aren't guessing, because they arrive at this number through several independent methods that cross-check each other. The expansion rate of space, the temperature of the cosmic microwave background, the age of the oldest stars we can observe. These lines of evidence converge on the same answer with remarkable precision, so the timeline is not in question. The universe is approximately 13.8 billion years old. That part is a confirmed fact. But what is being questioned is how much could happen within this timeline. Galaxy formation follows rules. Gravity is strong, but it's not instantaneous. Gas clouds need time to collapse. Stars need time to ignite. Galaxies need to merge and grow. None of this can happen instantly. That's why the models physicists built over decades were based on these limits. But Webb looked further back, and the timeline no longer fit. In 2023, a research team published an analysis of 6 galaxies imaged by Webb. All 6 were from within the first 700 million years after the Big Bang, and all 6 were far more massive than our models allowed for objects of that age. In fact, one of them was so far outside the expected parameters that the lead researcher told the press it caused sleepless nights. This is not the language of routine science. This is the language of a researcher looking at a result that should not exist. This mass problem gets even bigger when you add up all of Webb's observations. The total amount of stellar mass observed in the early universe appears to be roughly 10 times higher than what our best simulations produce. 10 times. This isn't a small calibration error. This is a structural problem with the model itself. But the timeline wasn't the only thing under pressure, because there's another, more fundamental number that has been causing controversy in physics for over a decade. And Webb just poured gasoline on that fire. This debate is about the rate at which the universe is tearing itself apart. In 1929, Edwin Hubble made one of the most important discoveries in science. He found that galaxies were moving away from us in every direction, and the farther away a galaxy was, the faster it seemed to be receding. This was the first concrete evidence that space itself was expanding. To describe how fast the fabric of space is expanding, scientists use a number called the Hubble constant. Getting this number right is one of the most critical tasks in all of cosmology, because it sets the scale for everything, from the age of the universe to the size of the observable universe. However, for decades, 2 main methods have been used to measure this number, and for decades, these 2 methods have been giving different answers. The first method looks at the early universe. It analyzes the cosmic microwave background. It calculates what the current expansion rate should be. This gives one number. The second method looks at the nearby universe. It uses exploding stars called Type 1a supernovae as distance markers. This gives a different number. The gap between these 2 measurements is called the Hubble Tension, and this tension is real. Because the 2 numbers disagree by roughly 9%. In everyday life, 9% might sound small. But in fundamental physics, 9% is a crisis. Because if both measurements are correct, and the evidence suggests they are, then either our model of the in-between evolution of the universe is wrong, or our understanding of how the universe evolved from that early state to today is wrong. It was hoped that Webb would resolve this tension. But the results published in 2024 were not comforting. Webb's measurements confirmed the discrepancy. The tension did not go away, but on the contrary, its increased precision made it even harder to blame measurement error. So, the universe is simultaneously expanding at 2 different rates, according to 2 different measurement methods. That sentence sounds absurd, but that's where the data points. At the center of all these problems lies a ghost, as old as the universe itself. You cannot see it, because it emits no light. It doesn't reflect light either. It passes through ordinary matter with almost no interaction. But we are almost certain it exists. The evidence comes from gravity. Galaxies rotate in ways that their visible mass cannot explain. Their outer edges should be spinning so slowly they fly apart. But instead, they rotate at roughly the same speed as the inner regions. This means there is something invisible and massive anchoring them. We call that thing dark matter, and it makes up roughly 27% of the total energy content of the universe. In our standard cosmology model, dark matter plays a critical role in galaxy formation. It forms invisible halos, massive gravitational seeds around which ordinary matter gathers. Gas falls into these halos on jinks, cools, and eventually forms stars. The dark matter halo is the skeleton. The galaxy is what's built inside it. But Webb is finding galaxies in the early universe so large that the dark matter halos that should host them shouldn't have formed yet. The scaffolding shouldn't have been in place. The construction couldn't have started. This is the dark matter problem that Webb has brought to the surface. It's pushing scientists toward a disturbing possibility. The possibility that dark matter is not what we think it is at all. And there's a piece in the Webb data that keeps leading researchers back to this uncomfortable door. It's not about what galaxies look like, but how they are arranged in the sky. Because the pattern they form is one that our best simulations consistently fail to reproduce. And now comes the real shock. Because what we've discussed so far were theoretical cracks in the models. But the Webb telescope didn't just challenge theories, it found evidence, visible, measurable, undeniable evidence. And each piece of this evidence shattered our story about the universe a little bit more. We now enter into those impossible findings, those numbers that caused sleepless nights, and those structures that should not exist. Buckle up, because the real journey begins now, and it all started with that first image, that famous deep field photo released on July 12th, 2022. Scientists expected to see young, messy galaxies, the baby steps of the universe. But that's not what appeared on the screen. What they saw were mature, huge, structured, brilliant galaxies. They looked like giants that had existed for billions of years. But they shouldn't have been there, because the light from those galaxies had started its journey when the universe was only a few 100 million years old. According to our current cosmological model, this was impossible. The laws of physics did not allow such large structures to form in such a short time. When one astronomer described the shock of analyzing the data this way, I opened a door expecting a small room and found a whole continent on the other side. This was not just an anomaly. This was the discovery of a continent not on any known map of the universe. So, the scientific community didn't panic. It recalculated. They checked the instruments. They went over the numbers again and again. But the result was always the same. Something was wrong with our picture of the universe. But this general shock paled in comparison to a specific object Webb found. Its name is GS9209. And this galaxy was impossibility made manifest, because this galaxy was dead. This is not a metaphor. In astronomy, a dead galaxy is one that has completely stopped producing new stars. It has exhausted its fuel and fallen into silence. And the problem is, according to Webb's data, or Deutsch GS9209, had formed all its stars in a period of about 800 million years, and it had completed this entire life cycle within the first 1.8 billion years after the Big Bang. Just think. Our own Milky Way galaxy is still actively producing stars after some 13 billion years. But GS9209 was born in an era when the universe was still in its infancy, grew up, created hundreds of billions of stars, and then fell silent forever. It was like a person being born, growing up, having a career, retiring, and dying of old age while their neighbors were still laying the foundations of their homes. We had no model for how such a thing was possible. So, scientists suggested that supermassive black holes might have quenched the galaxy. But for this mechanism to work so early and so quickly pushed the limits of current physics. Because GS9209 was not alone. This was a pattern of maturity that should not have been there. And this pattern pointed to an even bigger problem, the mass problem. This wasn't about the weirdness of a single galaxy. This was about the accounting books of the entire universe not adding up. With every observation, Webb kept finding more mass in the early universe than there should be. An analysis published in 2023 put this crisis into numbers. Researchers examined 6 galaxies imaged by Webb. All of them belonged to the first 700 million years of the universe, and all 6 were many times more massive than our models allowed for that age. One was so out of line that the lead researcher told the press it really caused sleepless nights. This was not a calibration error, because larger-scale studies confirmed this finding. The total amount of stellar mass we observe in the early universe is about 10 times more than what our best simulations produce. 10 times. That is not a rounding error. That is a declaration that there is a structural problem at the foundation of the model. Because, according to the laws of physics, there was no mechanism to bring together that much matter and turn it into stars in such a short time. The construction materials of the universe should have just been arriving at the site. But Webb was showing that the skyscrapers were already finished. Mature galaxies, giants that died before their time, and 10 times more mass than there should be. Each of these findings, even alone, was enough to shake the current model of cosmology. But when they all came together, a completely different picture emerged. Something was missing from the picture, or the picture itself was completely wrong. Scientists are now scrambling to explain these impossible observations. Should they revise the models? Or should they question what they know about the most fundamental laws of the universe? Because this problem of mass and timing inevitably leads us to another crisis. A famous tension that has been going on for a decade and which Webb has only deepened. The mind-bending problem of the universe expanding at 2 different speeds. And this problem is a knot that ties all these discoveries together, but also makes everything even more complex, because this tension points to an anomaly, not just in galaxies, but in the very fabric of space-time, one of the universe's most fundamental secrets. Because this tension is not just a numerical discrepancy, it's a mirror, showing 2 different faces of the universe, and Webb has made that mirror even shinier. The Hubble Tension has been plaguing cosmology for a decade. The expansion rate calculated from early universe data does not match the rate obtained from direct observations of the nearby universe. There's a difference of about 9%. This difference is too large and too consistent to be a measurement error. it was hoped that Webb would clarify this issue. Because Webb could measure Type 1, a supernovae, those cosmic distance markers that form the basis of nearby universe measurements, with unprecedented precision. But in 2024, the results came in, and they were not comforting. Webb's sharp eyes did not eliminate the inconsistency. On the contrary, they placed it on even firmer ground. The tension was real, and it was now impossible to hide behind the excuse of measurement error. So, science is now facing an unbelievable fact. The universe is simultaneously expanding at two different rates, according to two different and reliable measurement methods. This sentence is logically impossible. But the data insists on it. This means either our model of the early universe is wrong, or our evolutionary roadmap from that model to the present day is flawed. There is no other option. Because this is the most concrete evidence that something is missing in physics. But the oddities Webb found weren't limited to the galaxies themselves. The way galaxies are arranged, the cosmic architecture itself, also challenged expectations. When you zoom out far enough from the universe, a spider web appears, the cosmic web, giant filaments of gas and dark matter connecting galaxy clusters, and between them, vast voids where there is almost nothing. This structure was considered one of the greatest successes of our standard model, because our simulations produced a structure very similar to what we observed. But Webb began to complicate this success as well. Webb found surprisingly advanced galaxy agglomerations in the early universe. These are called protoclusters, the first seeds of future giant galaxy clusters. The existence of protoclusters was expected. The problem, was timing, and several protoclusters imaged by Webb were far more advanced than they should have been for their age. They contained more galaxies, they had a more organized structure, and they were more gravitationally bound. Imagine it this way. You're watching a city grow. The model tells you that after 10 years, you should see small villages. After 50 years, towns. But you look at the 10-year-old universe and see that the outlines of a metropolis have already been drawn. One confirmed example involves a structure from about 1.5 billion years after the Big Bang. In this young universe, Webb found that dozens of large galaxies were already organized into a cluster, with filamentary connections visible in the surrounding region. These structures shouldn't have existed at that age, and because there wasn't enough time for the gravitational force to work so quickly to bring them together. So, this was another failure of the standard model, and the failures kept coming. Perhaps the most surprising was an aesthetic problem, a problem of beauty, spiral galaxies, like our own Milky Way. These galaxies are not simple objects. They require a delicate gravitational balance, a stable disk, and most importantly, time, to maintain their arms for billions of years. So, astronomers were shocked when they started finding galaxies in Webb's deep field images that had no right to have this spiral structure yet. In 2022 and 2023, Webb photographed numerous galaxies with clear, organized spiral arms that existed just 2 to 3 billion years after the Big Bang. In that era, our models predicted that galaxies should still be irregular and chaotic, violently merging to assemble themselves. They shouldn't have settled into the elegant disk structures required for spiral arms yet. The light from one of these objects had traveled for more than 11 billion years to reach Webb. When it left its source, the universe was only a fifth of its current age. In a paper, they published Essig, researchers described their reaction to this discovery as unexpected and difficult to explain within current formation models. You know that it takes decades for rivers to carve their beds after the snow melts. But if someone showed you a picture of a fully formed, wide, lahai, and meandering river taken a week after the snow started melting. That's what Webb found. Rivers of stars, arterials, already carved into elegant spirals in an era when the formation process should have just begun. Impossible galaxies, a universe expanding at two different speeds, giant structures formed before their time, and spiral galaxies in their infancy. Every anomaly Webb has found points in one direction. Our story about the universe is incomplete. But these gaps are not just about what we see. They may also indicate that the fundamental mechanisms underlying all these structures, how the universe works, are also misunderstood. Because the invisible forces that feed, shape, and hold these giant structures together may themselves hold the greatest mystery. And now, it's time to delve into this invisible world, this cosmic engine, the secrets of dark matter and dark energy. So, how do all these structures work? What is the engine behind these impossible galaxies? Webb found these giant structures and these confusing patterns. It's time to move from shocking discoveries to the technical details that make these discoveries possible. Because, Laki, the secrets of the universe are hidden not just in what we see, but in how what we see works. Now, we will slow down the tempo a bit and take a closer look at some of the deepest and most invisible mechanisms of the cosmos. The key to understanding is to grasp this invisible world, dark matter and its dominion over the universe. Everything begins with dark matter. You can't see it. You can't touch it. But it makes up 27% of the universe. This is many times more than all the stars, planets, and gas clouds combined. Dark matter is the invisible skeleton of the universe. It is what holds galaxies together, what weaves the threads of the cosmic web. You can think of this mechanism as construction scaffolding. To build a skyscraper, you first erect a steel scaffold, concrete, glass, glassines, and all other materials are placed on this scaffold. This is exactly the function dark matter serves for galaxies. First, massive, spherical dark matter halos form. These are centers of immense gravitational pull. Then, ordinary matter, hydrogen and helium, gas, is drawn into this gravitational well. The gas cools inside this halo, condenses, and eventually ignites the first stars. The galaxy is born and grows within this invisible scaffold. Therefore, the mass and size of a galaxy are directly related to the mass of the dark matter halo that hosts it. The standard model predicts how these halos grow. They start small, merge, and grow over time. This accumulation process takes billions of years. That's why we didn't expect to see giant galaxies in the early universe. Because the dark matter scaffolds large enough to host those galaxies shouldn't have been built yet. But Webb's findings create a problem at this very point. Those giant galaxies found in the early universe don't fit into the scaffolds predicted by our models. This is like finding a finished skyscraper on the construction site the day after the groundbreaking ceremony. You don't doubt the existence of the skyscraper. You doubt the construction schedule. This is why scientists are now investigating three main possibilities. The first is that dark matter halos in the early universe formed more efficiently than our simulations predict. So perhaps the conditions immediately after the Big Bang allowed matter to clump together faster. This would be like the construction materials arriving faster and the workers being more efficient. The second, more radical possibility is that the behavior of dark matter was different in the early universe than it is today. Perhaps it had different properties at high temperatures, which allowed it to cluster faster. This would be like the concrete you're using, drying and hardening faster in the early stages. The third and most disturbing option is that dark matter is not what we think it is at all. This would mean the entire construction plan was based on the wrong material. This would require not just adjusting the model, but rebuilding it. Webb's data offers critical clues to test each of these possibilities, and scientists are carefully examining these clues. Alongside this invisible scaffold, there is also a mechanism that can end the life of galaxies. This is called quenching. This is the main theory proposed to explain early dying galaxies like GS9 209. You can compare this mechanism to a fire burning in a fireplace that is constantly being fed wood. The fire needs a continuous supply of fuel to keep burning. For galaxies, this fuel is cold hydrogen gas. Stars are formed from this gas. But when the supermassive black hole sitting at the center of the galaxy starts to feed, things change. When a black hole swallows matter, it radiates an incredible amount of energy into its surroundings. This energy passes through the galaxy like a storm and either pushes out the cold gas or heats it, making it unsuitable for star formation. In other words, the black hole kicks over the woodpile feeding the fireplace. When the fuel supply is cut off, new star formation stops. The galaxy quenches and slowly dies. This mechanism is confirmed to exist and operate in the nearby universe. However, the problem Webb found is how fast and how early this process can occur. According to our models, it should take billions of years for a supermassive black hole to reach a mass that can create such a powerful effect and then clear out all the gas in a galaxy. But galaxies like GS9 209 appear to have completed this process when the universe was less than 2 billion years old. This is like the fireplace suddenly cleaning itself and throwing out all the wood just as the fire has started to burn. So, either supermassive black holes grow much faster than we think, or the quenching mechanism works much more efficiently in the early universe. Both cases mean there is a huge gap in our standard story. Another critical mechanism in this story is the process of the universe itself becoming transparent, known as reionization. This is a major turning point in the history of the universe. For the first few 100 million years after the Big Bang, the universe was an opaque fog filled with neutral hydrogen gas. To clear this fog and make the universe transparent as we see it today, it was necessary to ionize those hydrogen atoms, that is, Chn, to strip off their electrons. The agent for this job was the intense ultraviolet, UV, light emitted from the first stars and galaxies. You can compare this to turning on many powerful projectors to illuminate a foggy room. Each projector clears a part of the fog, and when there are enough projectors, the whole room becomes bright. The standard model had a light budget that calculated how much UV light, how many projectors, were needed to do this job. This budget was based on known laws of atomic physics. But when Webb measured the actual UV output of early galaxies, it saw that the budget didn't add up. Many early galaxies were producing 3 to 5 times more ionizing radiation than the models predicted. In other words, the projectors we had were much brighter than we expected. This doesn't completely demolish the model, but it shows that our understanding of star formation efficiency within early galaxies is significantly wrong. Because such a high UV output means that the stars inside those galaxies were different from what we thought, are hotter, are more massive, and formed from gas with different properties. This both deepens the mystery of the first stars, population 3, and suggests that the entire chain reaction of galaxy formation may have operated faster and more efficiently than we thought. The invisible scaffolds of dark matter, the powerful storms of black holes, and the universe illuminating projectors of the first stars. Each of these mechanisms is a potential key to explaining the anomalies Webb has found. But each also brings new questions, because all these mechanisms are based on the most fundamental constants and laws of the universe. But what if those laws themselves have changed over time? What if the rules of the universe were not the same from the beginning? This is a possibility that could change the entire equation and push us into an even deeper, more fundamental inquiry. And Webb's data is bringing us right to the threshold of this unsettling possibility. Because light itself, one of the most fundamental building blocks of the universe, may be telling us an unexpected story about the past. Because this story forces us to question our most basic assumptions. The cosmic microwave background, CMB, the oldest light in the universe, gives us a snapshot of the universe when it was 380,000 years old. This is the universe's baby picture. The tiny temperature fluctuations in this picture contain the seeds of all the galaxy clusters and voids that would later form. You can compare this to tiny ripples on the surface of a calm lake. These ripples are the result of invisible currents beneath the water and determine where larger waves will form in the future. Our standard model predicted exactly what the temperature patterns in this baby picture should look like. And for years, the agreement between observations and theory was perfect. But when scientists started looking closer, they noticed some oddities, anomalies in the picture. For example, there was a large, cold spot, significantly colder than the rest of the sky. It's even stranger. The large-scale temperature patterns were unexpectedly aligned with a specific direction in space, an axis of evil. A universe born from a random explosion should not have a preferred direction, an axis, because the laws of physics do not prefer one direction over another. These anomalies were dismissed for years as statistical noise. But Webb's findings make it difficult to ignore this noise. Because if there are real anomalies in the CMB, and Webb is also finding galaxy structures that don't fit our models, maybe these two problems are connected. Maybe the seeds of galaxy formation encoded in that ancient light were not as random and simple as we thought. This would be like realizing that the ripples on the lake surface are caused not just by random winds, but by the movement of a huge, invisible structure under the water. This situation leads us to a radical idea that could solve all this complexity in one fell swoop, but could also demolish one of the most fundamental pillars of physics: an alternative theory of gravity. In 1983, a physicist named Mordechai Milgram proposed a framework called Modified Newtonian Dynamics, MMOND. This idea, largely ignored by the mainstream for decades, suggested that at very low accelerations, the kind experienced by stars at the outer edges of a galaxy, gravity doesn't exactly obey Newton's rules. According to him, gravity behaves stronger than expected under these conditions, so you can compare it to a rubber band that suddenly becomes much more flexible when stretched very slightly. At normal tensions, it behaves like a standard rubber band. But when a very weak force is applied, it stretches more than expected. Milgram's motivation was simple: galaxy rotation curves. Dark matter was invented to explain why the outer edges of galaxies rotate so fast. Milgram offered an alternative. Maybe there is no dark matter, and instead, the law of gravity itself changes. For years, this idea remained on the sidelines in the face of overwhelming evidence for dark matter. But Webb's findings have brought renewed attention to this old idea that because some small, isolated early universe galaxies observed by Webb show a rotation structure and stability that dark matter models cannot easily explain at that scale and age. In a few cases, researchers working within the MOND framework found that their own predictions matched the observed rotation profiles more cleanly than standard dark matter simulations. This does not mean MOND is proven, but it shows that the gap is closing in certain situations. If gravity is indeed stronger at low accelerations, galaxies could hold together with less mass, yet structures could form earlier, and disks could stabilize faster. This could naturally explain some of the anomalies Webb has found. However, MOND's biggest problem is that while it succeeds on the galactic scale, it struggles at larger scales like galaxy clusters and the cosmic web. That's why some theorists are now investigating hybrid models. Perhaps both dark matter exists and the law of gravity is modified. This is still a minority view. But, thanks to Webb, that minority is growing, and these growing doubts push us to question one of our most fundamental assumptions: the principle of the constancy of physical constants. Numbers like the speed of light, the strength of gravity, the charge of an electron, are called the fundamental constants of nature. It is assumed that the entire universe obeys these numbers, always and everywhere. But what if this assumption is wrong? What if these constants are not actually constant? This would be like a chef realizing that all the measurements in their cookbook, a cup, a teaspoon, etc., are slowly changing over time. You use the same recipe for years, but the results become increasingly different. Because your units of measurement have changed without you realizing it. Scientists can test this possibility by analyzing the spectrum of light from very distant objects like quasars. A number called the fine structure constant, which governs the strength of the electromagnetic force, is under particular scrutiny. Some analyses over the years have given hints that this constant might vary by very small amounts, less than 1% Ceres, in different directions of the universe. This was a spatially directional variation, the last thing you would expect from a universal constant. At Webb, ORCC, with its superior spectroscopic precision, is now testing these old hints. There are no confirmed results yet. But if a variation exists, Webb has the power to detect it. Because if fundamental constants were different in the early universe, this could explain many things in one fell swoop. Then, a 1 billion-year-old universe was a physically different place. The rules were not the same. Chemistry, atomic structure, the behavior of light, all operated under slightly modified parameters. This would instantly explain why early galaxies don't fit our models. Because our models assume that constants are constant. If they are not, every prediction made using those constants would be systematically wrong. This would mean that the laws of physics are not universal, but local and time-dependent. So these technical mechanisms, these radical ideas, They all show the complex landscape behind a door opened by Webb. The anomalies we see are not just simple calibration errors, but signs that something much deeper about the workings of the universe is wrong. The nature of dark matter, gravity itself, even the immutability of the laws of physics are now being questioned. This is the most exciting moment in science, a moment when everything is questioned. Every possibility is on the table. But what's truly exciting is that all these theoretical debates, all these technical details, lead us to a single conclusion. The universe structured itself faster, more efficiently, and more complexly than we expected. And now, it's time to witness the peak of this speed, this efficiency, the most violent and creative moments of the universe. We are now going to the most extreme environments Webb has taken us, to those hellish yet incredibly creative cosmic cauldrons where everything happens in top gear. Because the climax of the story, and now we come to the climax of the story. What we've talked about so far were cracks that shook the foundations. But now we will talk about the earthquakes that demolished those foundations. Webb didn't just question the rules of the universe. It found the places where the rules were completely broken. The most extreme environments, the most violent events, the most impossible objects. We're cranking the tempo to the maximum. So because now we are going to the darkest, most powerful, and most mind-bending places Webb has taken us. This is the moment science fiction becomes fact. This is the moment humanity confronts the universe. This is the moment everything changes. The first earthquake came from the darkest heart of the universe, supermassive black holes. We knew these monsters existed. But we had never seen their infancy. Webb changed that, and what it saw shattered all expectations. It was impossible. But it was real. Webb saw it. In 2023, the telescope detected an active supermassive black hole that existed when the universe was only 400 million years old. 400 million years, that's a blink of an eye on the cosmic timeline. In this period, Nutty, the first stars, should have just been starting to be born and die. But this black hole had already swallowed the mass of millions of stars. This was record-breaking gluttony. According to standard models, it was physically impossible for a black hole to grow this fast. Because there is a physical speed limit called the Eddington limit. It determines how fast a black hole can feed. This limit is based on the balance between the inward pull of gravity and the outward push of radiation pressure. This black hole seemed to have surpassed this limit. Or it had started as a massive seed from the very beginning. This was like trying to fill a swimming pool with a garden hose in 30 seconds instead of 30 hours. The hose has a flow limit, so you can't exceed it. So, you would need a much larger starting container or a completely different filling mechanism. This discovery sent a shockwave through the scientific community. Theories like direct collapse black holes suddenly took center stage in mainstream discussions. According to this theory, some giant gas clouds in the early universe skipped the star phase entirely and collapsed directly into black holes of thousands of solar masses. Webb did not prove this theory, but it provided the strongest evidence to support it, because the existence of this impossible monster showed that the story of galaxy formation might need to be rewritten from scratch. Perhaps black holes came first, holes, not galaxies, and galaxies were built around these dark kings, also exist independently. It meant that starless, Hubble-Tension dark worlds could be wandering in every corner of the universe. This was a possibility that could increase the number of potentially habitable worlds by trillions. Scientists still don't fully understand how these objects formed. But their existence proved that the universe is far more creative and flexible in creating objects than we thought. It was like realizing there was a page in the universe's rulebook that we didn't know about. And on that page, all completely new formation mechanisms were written. And the biggest earthquake, perhaps the most personal one, came from the atmosphere of a planet orbiting another star. The planet's name is K218b, a planet about 120 light-years from Earth, orbiting in its star's habitable zone, meaning liquid water could exist on its surface. Webb analyzed this planet's atmosphere, and what it found excited the scientific world and all of humanity. In 2023, Webb detected water vapor and carbon dioxide in the atmosphere of K218b. This was a huge discovery in itself. But the real bombshell was the potential signal of another molecule, dimethyl sulfide, DMS. On Earth, this molecule is produced almost exclusively by biological life, especially marine microorganisms. This was the strongest hint yet of a biosignature. A chemical proof of life. The researchers were extremely cautious. They stressed that the signal was not yet definitive and needed to be confirmed. But the very possibility was breathtaking. This was the moment in history we came closest to finding a potential chemical trace of life on another world. This wasn't just analyzing a planet's atmosphere. This was the most concrete step in seeking an answer to one of the deepest questions in the universe. Are we alone? We don't yet know if there is life on K2-18b. But Webb showed us that we not only have the ability to ask this question, but also the tools to answer it. This was a paradigm-shifting moment. The search for extraterrestrial life moved from philosophy to measurable science. And this transformation, thanks to Webb, is happening right now, before our very eyes, and the biggest earthquake of all, the most fundamental one, came from the very fabric of the universe itself. The cosmological principle. This principle states that on large enough scales, the universe looks the same in every direction and from every location. There is no special place, no special direction. All the equations of modern cosmology are based on this assumption. But Webb started finding patterns that question this principle too. The largest known structure, the Hercules Corona Borealis Great Wall, is a concentration of galaxies stretching for about 10 billion light-years. Considering that the diameter of the observable universe is about 93 billion light-years. This means a single structure is larger than 1/10 of the universe. This is impossible according to standard models. Because our models put a cap on the size of structures that gravity could have built within the age of the universe. That cap is roughly 1.2 billion light-years. The Hercules Corona Borealis Great Wall is almost 10 times this limit. The existence of this structure had been debated for years. But Webb has fueled this debate further by finding other large-scale concentrations and showing that galaxies are unexpectedly aligned. There are hints in Webb's deep field images that galaxies are aligned as if responding to a large-scale flow or structure not accounted for in our models. If the cosmological principle is wrong, even by a tiny amount, the consequences cascade through everything. the age of the universe, its expansion rate, not just dark energy measurements. They all rely on the truth of this principle. If you pull that thread, huge parts of the standard model need to be re-evaluated. This is to realize that not only is our map of the universe wrong, but the very paper the map is drawn on might be warped. This is a true intellectual crisis where scientists are forced to question even their most basic assumptions. The shocking birth of supermassive black holes, the discovery of starless planets, a potential chemical trace of life on another world, and giant structures that shake the most fundamental principle of the universe. Each of these discoveries is a revolution in itself. But when they all come together, they tell us one thing. The universe we thought we lived in was not the real universe. The real universe is weirder, bigger, faster, and operates by rules that push the limits of our imagination. So what does all this mean? What is humanity's place in this new, strange, esoteric, and mind-bending universe? Because the aftershocks of these scientific earthquakes are shaking not just laboratories and conference halls, but also our deepest philosophical questions about our own existence. Because these tremors are displacing not just scientific models, but also our perception of our place in the universe. What is this new universe telling humanity? This is just the beginning. Because Webb's most shocking findings are not just surprising us, they are also offering a completely new perspective on the universe's most fundamental creative processes. This is a moment to rethink not just what exists, but existence itself. Now, we go beyond the limits of science for one last dive into the universe's most primitive, most powerful, and most mysterious moments. The very first moments where it all began. Because the greatest secret may be hidden at the very beginning. And that secret at the very beginning lies in the universe's first stars. They are called Population 3 stars. They were a legend. No one had seen them. But they had to exist. The first lights of the universe. The first sparks that ended the 200 million year cosmic dark ages after the Big Bang. Theories said they were giant, hundreds of solar masses, hot, blue, and furious monsters. They were supposed to live for only a few million years and then explode in violent supernovae, seeding the universe with the first heavy elements: carbon, oxygen, and iron. They were the ancestors of every carbon atom in your body. But this was just a theory, until Webb looked. Webb could not observe these legendary stars directly, not yet. But it saw the chemical traces they left behind with incredible clarity. It analyzed the spectra of galaxies in the early universe, and what it found was another shock. These primordial galaxies contained much higher levels of heavy elements than expected. This chemical enrichment had happened much faster than our models predicted. This was the first direct evidence in history that the chemical evolution of the universe was more efficient than we expected. It meant the first furnaces were not only more numerous, but also burned hotter. Population 3 stars must have been not just massive, but unimaginably massive and far more numerous. This pulled the entire chemical evolution timeline forward. It meant the building blocks of planets and life were abundant in the universe much earlier than we thought. This discovery created a revolution in the scientific world, because it meant we had to rethink not just galaxy formation, but also the origins of cosmic habitability. The universe was in no hurry to produce the materials necessary for life. On the contrary, it worked with incredible speed and efficiency. But the biggest shock Webb found was perhaps the quietest one. the most invisible: dark energy itself. This mysterious force, making up 68% of the universe, is accelerating the expansion of space. In the Standard Model, dark energy was a single value, called the cosmological constant, that did not change across time and space. But this was a theoretical nightmare, because its value calculated using quantum mechanics was unimaginably larger than the value we observe, by 120 orders of magnitude. This was the biggest discrepancy in the history of science. It was called the vacuum catastrophe. Webb began to help solve this mystery by observing very distant supernovae with unprecedented precision. It tested whether dark energy was truly constant, and the initial results were the harbingers of another earthquake. The data, though not yet conclusive proof, favored a scenario where dark energy was not perfectly constant, but its strength might have changed slightly over cosmic time. This was the first concrete observational hint in history that dark energy might be dynamic. If this is confirmed, the idea of a cosmological constant would collapse. It would mean dark energy could be a field that evolves over time, called quintessence. This would not only change all our predictions about the future of the universe, but also fundamentally shake our understanding of its past. Because if dark energy can change, then other things we assumed were constant might change too. This was like realizing that the rules of the universe were not written in stone, but in sand, and the wind was constantly reshaping them. This possibility both excited and terrified physicists, because it meant the fate of the universe might be far more uncertain and far more interesting than we thought. And this uncertainty brings us to Webb's most jarring and philosophical finding. It's not a single object or a single measurement. It's a pattern formed by the convergence of all observations. A crisis, yet a situation that scientists privately call the crisis of cosmological precision. The idea is this: as our instruments become more precise, they reveal not only the answers our models predict, but also exactly where and how those predictions fail. Precision doesn't just show us the universe more clearly, it also more sharply reveals the limits of our understanding. The Hubble Tension. A 9% mismatch between two different measurements. The early galaxy mass problem. A 10-fold discrepancy. These are not small calibration errors. These are cracks in the structure itself. This situation has led to a deep intellectual and professional crisis in the scientific community. Senior researchers who have built their careers on the Standard Model now feel the foundations of their life's work shaking. And many describe it as a vertigo, like the ground you trust slipping from under your feet. At conferences, fierce debates are taking place that were never before public. This is a sign that science is working healthily. But it is also an indication that we are experiencing the birth pangs of a major paradigm shift. Because history has taught us that when so many structural problems accumulate in a scientific framework, the solution is not a patch, but a whole new framework. Right now, there are at least 4 serious theoretical groups trying to build this new framework, and they are all competing to explain Webb's data. This is the most chaotic, but also the most productive moment in science. This is the moment when you think you have almost completed a jigsaw puzzle. And then you realize that the new pieces you have don't fit anywhere in the picture. Now the puzzle makers are debating whether these new pieces belong to another picture, or whether the original picture needs to be dismantled and rebuilt around these new pieces. Webb gave us those new pieces, and now, The whole picture needs to be redrawn. All these earthquakes, all these shocks, all these crises, this new, wild, and rule-breaking universe that Webb has shown us. It leaves us with one final question. So what does this mean for us? In this unimaginably large, this incomprehensibly complex cosmos, what is the place of this curious species on a speck of dust? It's time to stop running at maximum speed, to pause for a moment, to breathe, and to think, as because. Webb's final and perhaps greatest discovery is not about numbers or graphs. It's about seeing our own reflection in the mirror. It's about re-questioning what it means to be human in the midst of all this cosmic drama. Because the final act of this story is not about numbers and theories. It's about meaning. And now, in the midst of all this cosmic noise, it is time to stop and ask ourselves the most fundamental question. All these discoveries, this 93 billion light-year diameter observable universe, this 13.8 billion year history, these rule-breaking galaxies and these invisible substances, what does it all mean for us? We are not accelerating anymore. We are slowing down, because the greatest lessons of the universe are learned not in its fastest moments, but in its quietest. Now, within this new reality Webb has presented to us, we embark on a philosophical journey about what it means to be human. The first and most obvious confrontation is with scale. On one hand, there is an unimaginable vastness where words and numbers fail. It takes light 93 billion years to travel from one end of the observable universe to the other. It's estimated to contain at least 2 trillion galaxies like our Milky Way. Each galaxy has hundreds of billions of stars. This means there are more stars in the universe than all the grains of sand on Earth. On the other hand, there is you, an approximately 1.7 meter tall, carbon-based, delicate life form. In this vast cosmic ocean, you occupy a space smaller than an atom. How can such a microscopic being have any meaning in such an overwhelming vastness? This is our most fundamental existential paradox, and there is a tragic side to this paradox, and it is this: physically, we will never reach those distant lands. Even the closest star system, Proxima Centauri, is tens of thousands of years away with our fastest spacecraft. Going to the Andromeda Galaxy would take millions of years. Reaching those first galaxies Webb showed us is literally impossible, because they are moving away from us faster than light. We live on a small, isolated island, separated from the rest of the universe by an insurmountable ocean of emptiness. This is a deep sense of cosmic loneliness that fills one with melancholy. But it is at this very point that the word "but" comes into play, because even though we can't go there physically, we go there with our minds, with our science, with our telescopes. From where you sit, you can look at the light of a galaxy that existed 13.4 billion years ago. You can understand something you cannot reach. This is the greatest miracle of human consciousness. We are not just a part of the universe, we are the part of the universe through which it observes itself, understands itself, and marvels at itself. Therefore, the size of the universe is not there to crush you, but to remind you of the incredible ability you possess. You are that tiny, but priceless point in this vast universe that creates meaning. The second confrontation is with time. On one hand, there is a cosmic history of 13.8 billion years, which seems almost infinite. The birth of the universe, the shining of the first stars, the formation of galaxies, a slow and majestic evolution lasting billions of years. On this timeline, the entire reign of the dinosaurs is but a fleeting moment. The whole of human history is a sound lost between the ticks of that cosmic clock. On the other hand, there is your life, an average of 80 years, a fleeting and fragile existence that passes in the blink of an eye. How can such a short life leave a mark in such an overwhelming chasm of time? This is the temporal paradox of existence, and this paradox also has a tragic side, and it is this: cosmically speaking, we are nothing. When we were born, the great story of the universe had already begun long ago, and it will continue for billions of years after we die. We are like an extra in this huge theatrical play, who comes on stage for only a few seconds, without even a line. This can lead to a deep anxiety, making us think how meaningless and temporary our existence is. But again, that magic word comes, but, because yes, we are here for only a moment. But that moment can be the moment that changes everything, because that short human life is long enough to experience all the wisdom, all the material richness that the universe has accumulated for 13.8 billion years. In your short life, you have a body made of elements forged in the hearts of stars that died billions of years ago. You breathe oxygen. You carry iron. You think with carbon. You are a cumulative result of the universe itself. Therefore, the shortness of time is not a curse, but a blessing, because it makes every moment more precious, every experience more meaningful. You are that unique and unrepeatable moment in which the 13.8 billion year story of the universe is crowned by your existence. You are the most precious jewel of time, carrying within you all the accumulation of the past and all the potential of the future. The third and perhaps deepest confrontation is with knowledge. On one hand, there are the incredibly successful and precise models that science offers us about the workings of the universe. Theories like the lambda, cold, dark matter model have explained the large-scale structure of the universe, the distribution of galaxies, the cosmic microwave background with incredible accuracy for decades. This was a tremendous victory for the human mind's ability to solve nature's deepest secrets, so we were beginning to think we understood almost everything. On the other hand, there is the reality that Webb slaps us in the face with every day. We actually know almost nothing. We don't know what 95% of the universe is. We see that even the remaining 5%, the part we thought we knew, doesn't behave as we expected. How can we be so knowledgeable and at the same time so ignorant? This is the ultimate paradox of knowledge, and the tragic side of this paradox is a lesson in humility that shatters human hubris. We realize how shaky the foundations of that magnificent tower of knowledge, built by our brightest minds and most advanced technology, actually are. Every answer brings 10 new questions. Every new island we discover in the ocean of knowledge only makes us realize how much bigger the ocean is. This can create a feeling that we are in an endless search that will never reach a conclusion. But here lies the most beautiful but of this story. Because the purpose of science is not to know everything and close the book. The purpose of science is to keep wondering. The greatest favor Webb has done for us is not to give us definitive answers, but to inspire us to ask better, deeper, and more exciting questions. It reminded us that saying, "I don't know," is not a weakness, but the greatest intellectual virtue. You are a part of this process too. With every question you wonder about, every answer you doubt, every new piece of information you marvel at, you too participate in this great human adventure. The quest to understand the universe. There is no end to knowledge, and this is not a reason to despair, but the greatest good news, meaning we can wonder and learn forever. Scale, time, and knowledge. These three great confrontations draw the philosophical framework of the new universe that Webb has presented to us. But within this framework, there is another dimension, more personal, more poignant, and perhaps more important. It is about how we connect with each other in the midst of all this cosmic loneliness, this overwhelming vastness, and this deep ignorance. Because the universe doesn't show us how big we are. Because the universe doesn't show us how big we are, but how interconnected we are. The fourth confrontation is about loneliness and togetherness. On one hand, there is the overwhelming cosmic void that Webb shows us, millions of light years of near absolute zero coldness and darkness between galaxies. Each galaxy is a community of light, existing in isolation on its own gravitational island, hopelessly distant from the others. This gives the feeling that the universe is a fundamentally lonely place. Each of us can feel as if we are drifting alone in this vast emptiness, inside our own consciousness. On the other hand, there is the existence of the stars, suns, planets, and living beings like you and me within those galaxies. We all came into existence from the same basic materials, under the same laws of physics, as a result of the same cosmic history. How can there be such a deep connection in such an isolated universe? This is the most poignant paradox of existence, and the tragic part of it is that we often fail to see this connection. In the rush of daily life, we perceive ourselves as individual beings, separate from others and from nature. But this is an illusion that is tragic at the atomic level. Because each of us is literally stardust. Every heavy atom in your body was forged in the heart of a star billions of years ago and scattered into space by a supernova explosion. You, me, every living thing on this planet, we all come from the same cosmic ancestors. We are connected to each other and to the universe in a way that is much deeper and more fundamental than we can imagine. Those distant galaxies that Webb shows us are not foreign and unreachable lands. They are our distant relatives, our cosmic cousins, abats, born from the same beginning, the same physical processes. You are part of this great family. When you look at another person, touch a tree, or look up at the sky, you are actually seeing a different reflection of your own cosmic origins. Loneliness is an illusion. Connection is the most fundamental truth of the universe. And the final confrontation is about power and fragility. On one hand, there are the unimaginable forces that govern the universe. A supernova releasing more energy in seconds than our sun will in its entire lifetime. The gravitational pull of a black hole that can swallow even light. The unstoppable expansion of dark energy that pushes billions of galaxies apart. Compared to these forces, we as humanity are extremely weak and fragile. The impact of a single asteroid could destroy our entire civilization. A small change in our sun could end life on our planet. Here we are extremely delicate beings at the mercy of cosmic forces. On the other hand, there is the human mind, capable of understanding, measuring, and even to some extent predicting all these forces. With our minds, we write equations, form theories, and build machines like Webb to try to solve the deepest secrets of those forces. How can a species so physically weak be so intellectually powerful? This is the ultimate paradox of the human condition, and the tragic part of it is that our knowledge is not proportional to our power. Even if we understand how the universe works, we cannot control it. We cannot change the orbit of a galaxy. We cannot prevent a star from dying. We cannot determine the ultimate fate of the universe. We are the most intelligent, Naoj, but also the most powerless. Children of the universe. This can lead to a sense of helplessness. But it is at this point that the most hopeful but comes, Bay, because our power lies not in controlling the universe, but in appreciating it. Our power is not in our muscles, but in our consciousness. Our task is not to rule the universe, but to bear witness to it. And this is a much nobler and much deeper task. You, within your weak and mortal body, carry the sacred space where the universe questions itself, marvels at its own beauty, and contemplates the mystery of existence. This is the greatest power given to you. Your physical fragility makes your mental strength even more valuable. Because you are that rare and priceless spark in this infinite and sometimes frightening universe that creates meaning, sees beauty, and asks questions, such after all these confrontations. In the light of all these paradoxes, now ask yourself this question: how do you feel after learning all this? On one hand, is there that feeling of smallness, meaninglessness, and cosmic loneliness you feel in the face of the universe's overwhelming size, the ruthlessness of time, and the depth of our own ignorance? Or on the other hand, is there that sense of wonder, connection, and deep meaning you feel in the face of the miracle of human consciousness, which can comprehend this vast universe? Fit billions of years of history into this short life, and show the courage to wonder in the midst of this deep ignorance. You probably feel both, and that is perfectly normal. Because these two feelings are two sides of the same coin. To be human is to live right in the middle of this tension. It is to know at the same time that we are both as insignificant as a speck of dust and as meaningful as a universe. It is to feel that we are both tragically alone and miraculously interconnected. Webb's greatest gift to us is that it has shown us this tension, this paradox, with the sharpest clarity ever. It did not give us an answer. It reminded us what the right question is. And the right question is not, what is the universe, but who are we within this universe? As we approach the end of this long and dizzying journey, we now know the universe we thought we lived in was not the real universe. The real universe formed faster, more efficiently, and more complexly than our models predicted. It is a weirder, bigger place with more flexible rules. We now know that we have no idea what 95% of the universe is, and we have understood that even the 5% we thought we knew is full of secrets. We now know that the moment we thought we had reached the pinnacle of our scientific knowledge, Yuan, is actually the moment we realize how little we know. But most importantly, we now know that despite all this overwhelming vastness, this deep mystery, and these jarring truths, our quest to understand the universe is humanity's noblest and most meaningful adventure. This journey does not end here. On the contrary, it is just beginning. Because every door Webb has opened has shown that there are dozens of new doors behind it. And behind those doors, new worlds, new questions, and new realities we cannot even imagine are waiting for us. And now, in the light of all this information, we face one last question. What does this whole story tell us about our future? In this video, we saw how Webb destroyed our universe. But I didn't tell you one thing. What if all these anomalies are not from an error, but from a design? Those strange inconsistencies in the laws of physics, the galaxies that arrived too early, the shifting of cosmic constants. Could they all be traces of a simulation? In the next journey, we will question reality itself. Are we in the Matrix? Are you ready?